check in with our schedule here. We are moving on from exponential functions. Today we're going to talk about logarithmic functions. So this is probably something you have never heard of. Okay, so this will be brand new. Quiz 6 is being assigned today. Take home quiz 6. It's due on Friday. Covers lectures 31 to 35. I'll give that out after the demo portion of class. And then we only have 2 more classes before the test, right? So today is the last, that's not true. Everything will be on, that we cover before the test will be on the test. So today and Friday are our last 2 days of material. We'll review on Monday and take test 3 on Wednesday. Questions about the schedule? And then that will be our last thing other than project 5 and the final exam. And project 5 is really just a review for the final exam. All right, so let's look at class 35, log functions. Do you guys remember the switch and solve strategy when you're trying to find the inverse of a function? The first thing you did was replace the f of x with a y. Then you make all the y's x's and the x's y's. So it was x equals 2 to the y. And then the last step is to solve for y, right? No, it's the packet that we were working out of before that starts with quadratics. Yeah. Because I had to give you that insert for 33 and 34. All right, so I have x equals 2 to the y, and I need to now solve for y. How do you get that y by itself? Math. Good answer. That's for negative exponents, yeah. Yeah, we actually don't have a tool to do this, right? So typically, if it was a number up there, you could take an appropriate root of both sides, right? If that was a 6, you could take the 6th root. But it's not, it's a y, and what does it even mean to take the y-th root of something? Like, it doesn't make any sense. So at this point, we're stuck, right? We are stuck. We have to solve 2 to what power equals x, right? So let's maybe if we use some numbers first instead of all just letters, right? So 25 to what power would give you 5? That is, I want to solve 25 to the x equals 5. A half. Yeah, 25 to the x equals 5. The power that you raise 25 to get 5 would be 1/2, right? Because raising to the 1/2 is the same thing as square rooting. Square root of 25 is 5. All right, so this is the kind of thing we're going to be learning how to do. We're figuring out when the thing that you don't know is in the exponent, how do you deal with that? Yeah, the answer is logarithms. All right, so brief summary about inverse functions. So we talked about this quite a while ago now, but they have come up multiple times throughout the course. Only a one-to-one function has an inverse that is also a function. And you test to see if a graph is one-to-one by using the horizontal line test. If a function is one-to-one, its inverse function can be found by doing the switch and solve, right? Switch all the x's and y's and solve for the y. The domain of a function is the range of its inverse, and the range of a function is the domain of its inverse. So if the x's and y's swap, then the domain and the range are going to swap. The graph of f inverse is the reflection of the graph of f along the line y equals x. So to get points on the graph of f inverse, you just swap the coordinates, swap the x and the y coordinates that are on the graph of f. And because inverse functions undo each other, when you compose them, when you compose 2 inverse functions, you always get the x back, right? This is like a round trip. You put x into f, apply the function f to the number x, and you get something, and then you apply f inverse to it, and you get the x back. All right, so that's my very brief summary of inverse functions. All right, so remember last class, we were looking at exponential functions that look like b to the x, they're 1-to-1, right? And these are the two flavors, right? We've got exponential growth and exponential decay. Both of them pass the horizontal line test. Okay, so it is 1-to-1. Both of these are 1-to-1. So since an exponential function is 1-to-1, we know it must have an inverse function. That's what it means to be 1-to-1. Its inverse is also a function. So I want to sketch the graph of the inverse of 2 to the x. I just graphed 2 to the x there. I want to sketch its inverse. I don't want to find its formula yet. I just want to try to draw it. So remember that inverses are reflections over the line y equals x. So I'm just going to put the line y equals x in here. So that's just a line with y-intercept 0, slope of 1. Okay. And then I want to draw the mirror image of the graph I have, 2 to the x, mirrored on the other side of the line y equals x. So one way to help you do this, remember, is to just pick some nice points on the graph. Yeah, my line's not perfect, I'm sorry. One way to do this is to just pick some nice points on the graph and swap their coordinates. So let's see, are there some easy places, like right here, that looks like it goes through the point 0, 1. I'll list them over here. And then that point right there looks like 2, 4. And then there's a point on a grid right there, 3, 8. And maybe I have one more right here, 4, 16. And it might help if I just get at least one negative x. Like it's not on a perfect grid point, but that point right there looks like -1, a half. This point right here, over 4, up 16. Oh, turn the page. There you go. Turn the page. Okay, so now if I want to try to plot the inverse, I'm going to just reverse all of these coordinates. Instead of 0, 1, I'm going to plot the point 1, 0. So that's going to land right there. And then instead of 2, 4, I'm going to plot 4, 2. And instead of 3, 8, 8, 3. And instead of 4, 16, 16, 1, 2, 3, 4. And instead of -1, a half, I'm going to plot 1/2, -1, just like right there. And if I try to connect those with a nice smooth curve and knowing that it has supposed to be the mirror image of my graph of 2 to the x, I'm going to get something like this. And this would go down like that. Yeah, I got an asymptote. So that is the inverse. This is f inverse of x, right? If f of x equals 2 to the x. It's the inverse. We drew it. So it exists, and it's kind of pretty. Has an inverse. We can look at its graph. The question is, what about its formula, right? Can we come up with a formula for that green function, the inverse of 2 to the x? So to find the inverse, we start with 2 to the x, we interchange the x and the y, and we solve for y. So we start with f of x equals 2 to the x. We replace the f of x with a y. We swap the x's and the y's. Every y becomes an x, every x becomes a y. So I now have x equals 2 to the y. That's what we did earlier. And now I have to solve for y. But uh-oh, I don't have a mathematical way of getting the y by itself in that equation. We need a way to undo 2 to the something, right? How do you undo raising 2 to some power? So the name of the function that undoes 2 to the y, we're just going to name it log base 2 of y. Okay? Why we came up with that name, I don't know. but it's just the name of the function that undoes 2 to a power. Okay, so if I were going to finish what I was doing here, I would write x equals 2 to the y. And to undo 2 to the y, right, undoing 2 to the y means I want to get the y by itself. The thing that will get that y by itself is to take log base 2. So I'm going to take log base 2 of both sides here. Log base 2 of x equals log base 2 of 2 to the y. Okay. And log base 2 is the thing that undoes 2 to the y, right? So log base 2 of 2 to the y undoes it. So I now have log base 2 of x is equal to log base 2 of 2 to the y is y. Log base 2 is the thing that gets the y by itself. It's just a name of a function that says if you have 2 to a power and you want that power by itself, we're to take the log of it. So that yeah. No, so what I did is I'm going from this previous step and I just copied the left-hand side. And the right-hand side, log base 2 undid 2 to the y. So the y ended up by itself. Oh, then yes. Yeah, yeah, yeah. So this is the inverse of 2 to the x. This is f inverse of x. That is the inverse function of 2 to the x. So we already had a picture of it. We just needed to name it, right? So it's named log base 2 of x. That's an equal sign, log base 2 of x. That's the name of that green function. Okay, so I know that that's a lot to take in all at once. All right, so let's just start again talking about the logarithm, the definition of a logarithm. Okay. So y equals log base b of x is an equivalent way of saying that b to the y equals x. Just like saying dividing by 5 and multiplying by 1/5 are equivalent ways of doing the same operation, right? So I could, and because multiplication and division are inverse operations, right? So dividing by 5, multiplying by 1/5, they undo each other. So log base b of x equals y. That means the exact same thing as b to the y equals x. So I think if we do some things with numbers, this will get a little clearer. All right. Different ways of expressing the same thing, just like saying 10 over x equals 5 is the same equation. That equation is equivalent to 10 equals 5x, right? You could just multiply both sides by x, get an equivalent equation. These things are equivalent equations. All right, so some numbers. I have a couple of sentences involving logarithms here. I want to convert them to equivalent equations that instead of using logarithms, they're going to use exponents. So I'll just remind you up here, log base b of y, how did I write it? Log base b of y of x equals y. Log base b of x equals y is equivalent, that double arrow means equivalent, is equivalent to b to the y equals x. All right. So what is the base in this logarithm on the right? 3. Okay. So the number on the other side of the equal sign in this formula, log base b of x equals y, b is the base in the logarithm, and it's also the base in the exponential, right? So it's a good reason we called it b, right? It's the base of the logarithm, and it's the base of the exponential equation. The exponent in the log equation always appears by itself on the other side. It becomes the exponent in your exponential. So the x and the y basically swap places, right? B is with x in the logarithm, and it's with the y in the exponential. And it makes sense that they would swap places because these are inverse functions. They swap the role of x and y, right? All right, so my base is going to be 3. What's my exponent? 2. And that should equal 9. Is that a true statement? Yes. Okay. All right. Yep. Yep. All right, so in this next one, my base is 8. What is my exponent? -1. And that should equal the final number in the equation, 1/8. Is that true? Yes. 8 to the -1 does equal 1/8. All right, so we can go from logarithmic to exponential form. Now, if I give it to you in exponential form, we should be able to go the other direction and write it in log form. Log, I'm going to have something here, and something here. All right, what's my base? 2. The base in the exponential is 2. It's also going to be the base in the logarithm. Okay. And then basically, the 3 in the exponential, it's paired with the 2. It's not going to be paired with the 2. It's going to swap places. So this is going to be 8 and 3. The exponent is always by itself in the log equation on the other side of the equals. All right, so in this one, 6 to the -2 is 1 over 36. An equivalent way of saying that would be to take the log. What base would I use? 6, because that's the base in the exponential. Log base 6 of something equals something else. The exponent always goes on the other side of the equation, so that would be -2. And then you put the final number in there. All right. So now we're going to get a little more trickier. We're not just translating because I didn't give you what it equals, right? That's the question. What does that equal? Okay. So this is log base 10 of 100. So if I wanted to write that as an exponential, we don't know what it equals, right? That's the question. We don't know what the log base 10 of 100 is. Yeah, so if I was going to translate this to an exponential equation, my base would be 10. My exponent would be x, and my number on the other side would be 100, right? What number do you raise 10 to make a 100? 2. X, yeah. So the answer is 2. Log base 10 of 100 is 2. So you can read that. You could translate it every time, or you can learn to read this as log base 10 of 100 means what power do you raise 10 to make 100? Okay. So let's do the next one that way. What power do you raise 5 to make 1 over 125? -3. It's got to be negative, yeah, to flip the fraction. And 5 cubed is 125, yeah. What power do you raise 36 to make 6? A half. Yeah. And if it ever trips you up, just say, okay, the thing I don't know is the right-hand side of the equation. Just make it an x, and you can translate it to an exponential expression. This says 36 is my base, x is my exponent, equals 6. What power do you raise 36 to make 6? 1/2, because the square root of 36 is 6. All right, I know it's a lot to take in because it's a brand new function and brand new notation to go with it, but the best thing you can do is just try to do some stuff with it right now.